Today's topic is going to be centered around the study of the one-dimensional motion. And more specifically, it's going to be focused on the study of the free fall type of motion. So what's a free fall motion? How can we define the state of a free fall? Any object that is being acted upon only by the force of gravity is said to be in a state of free fall. So a free-falling object is basically any object that is falling down under the sole influence of its own weight. In other words, under the sole influence of the force of gravity. So the only force which is acting upon an object in a state of free fall is the force of gravity, without the interference of any other external force. However, such very particular definition of a free fall motion is actually associated with two important characteristics, meaning that in order to identify the state of free fall in such way where the only force acting upon an object in a state of free fall is only the force of gravity, therefore there are two characteristics that should be considered in order for that definition to be valid. What are these two characteristics? In many physics problems that actually deal with a free fall motion, they cancel out one major aspect of the problem, which is the presence of drag forces. Drag forces meaning the presence of resistive forces such as air resistance. So they consider that the object which is undergoing a free fall motion is actually encountering very minimal resistance from air molecules, and therefore they cancel air resistance out, and in that case the only force acting upon the object would be the force of gravity. However, in reality that is not correct, because for the majority of free fall motions you have presence of drag forces, or you have presence of air resistance at least. And air resistance in that case would be acting in the opposite direction of the motion, or in the opposite direction of the force of gravity. So air resistance would be hindering the motion. It would be decreasing the speed of the object which is undergoing a free fall motion. For example, if we consider a skydiver who's actually jumping from a very high altitude, therefore the skydiver is going to be encountering major air resistance or major drag forces. However, right at the beginning of the motion, the speed of the skydiver is going to be minimal, and for that minimal speed we are going to have minimal air resistance. But why in that case? Air resistance, it arises from the collisions between air molecules and the skydiver's body. So right at the beginning of the motion, since we have minimal velocity, therefore we don't have frequent collisions between air molecules and the skydiver's body. Therefore we have minimal air resistance. So the less frequent the collisions are between air molecules and the skydiver's body, therefore the lesser the magnitude of air resistance is going to be. And in a similar manner, the higher the speed is going to be, therefore the more frequent the collisions are between the air molecules and the skydiver's body, and therefore the greater the magnitude of air resistance is going to be. So right at the beginning of the motion, since we have a minimal velocity for the skydiver, therefore we have a minimal drag force acting upon him or acting against his motion. Now if we have a look at the body force diagram on the left side, we can clearly see that now after a certain time it has elapsed after the skydiver jumped, therefore his velocity it incremented. And for that increment in velocity we have a corresponding increment in drag force and air resistance. So as we can see on that body force diagram on the left side, we can clearly see that the letter D, which represents drag force, now it has a significant magnitude. It has incremented over time. And then countering that drag force, we have none other but the weight of that skydiver. Now after a long time has elapsed, the skydiver has reached a certain maximum velocity. And for that maximum velocity, now the magnitude of the drag force, it has become significant enough in order for it to be equal to the magnitude of the weight. So after a certain time, and as the speed of the skydiver kept on incrementing over time, we have reached a certain point where the magnitude of the drag force is now equaling the magnitude of the weight of the skydiver. And therefore, for that condition, the skydiver has reached a terminal velocity. So what's a terminal velocity? A terminal velocity is a maximum velocity. It's a maximum and constant velocity for which the drag force is equal to the weight. And moreover, the acceleration of that skydiver now is equal to zero. He's no longer accelerating. So if we have a look at the following brick over here, let's say that that brick is being dropped from a very high altitude. Therefore, there are two forces acting upon that brick. You have its own weight, the brick's own weight, which is a vertical and downward force, and then over here you have the drag force or air resistance, which is acting in the opposite direction of the motion. So after a certain time, when the speed of that brick becomes significant enough, therefore the drag force over here, the magnitude of the drag force, is going to be equal to the magnitude of the weight of that brick. So for that condition over here, the brick has reached a terminal velocity, meaning its velocity is going to reach a maximum value and stabilize and becomes a constant. And moreover, the acceleration of that brick would be equal to 0 for a constant velocity. So over here, if we want to find the summation of all the forces which are acting upon that brick, the summation of all the forces in that case is actually equal to 0. Because as we can see, we have two forces which are acting upon that brick, but these two forces, they have the same magnitude and they are directed in the opposite direction. Therefore, they cancel each other out. Moreover, if you want to represent graphically the relationship between velocity and time in that case. So, as I have said, that velocity is actually varying with time. So the moment that brick is being thrown, is being dropped, it started at a certain velocity, however, it ended at a totally different velocity, which is a terminal velocity. So at the beginning, like I said, the velocity is going to be minimal. Therefore, the corresponding drag force is also going to be minimal. But first off, over here, before we start drawing, you have to assign a certain direction for the positive y direction. Usually, the positive y direction is taken to be the upward direction. However, that direction can be totally individual and arbitrary, meaning you can take the positive y direction to be also the downward direction. Now, since I have taken the positive y direction to be the upward direction, I'm going to be drawing the relationship between the velocity and time in that negative compartment over here. Since we have a motion which is directed downwardly, and over here I have chosen the positive y direction to be the upward direction. So like I said at the beginning, once the brick enters into motion, its velocity is going to be minimal, and therefore the corresponding drag forces acting upon it are also minimal, almost negligible. Therefore, the relationship between the velocity and time is going to be a linear relationship. So the velocity is steadily increasing over time. So that linear relationship over here implies that the velocity is steadily increasing over time, but moreover, that brick over here, it has a constant acceleration. So the slope of v versus t over here is none other but the acceleration. So over here that implies that the brick, it has a constant acceleration. However, as the velocity keeps on increasing over time, therefore the drag force over here, the magnitude of the drag force, is going to become much more significant. And in that case, this is going to affect that linear relationship over here by curving it. So now the relationship between v and t is going to start to curve until we reach a certain point where the weight is equal to the drag force. And for that condition over here, we are reaching a terminal velocity or a constant velocity. So that curve over here, or that graph, is going to keep curving until it flattens out. Once it flattens out over here, meaning that we have reached a terminal velocity for which the weight is equal to the drag force. So as you can see over here, first off, we started with a linear relationship between v and t. However, that linearity didn't last long, because now we have the drag force coming into play and therefore affecting that linearity between v and t. And therefore, that graphical representation, it started to curve until it flattened out at the end once we reached a terminal velocity, meaning a constant velocity. And for that terminal velocity over here, the acceleration is actually 0. Now, in our case today, in our experiment, the experiment is going to be done within a certain closed space. Therefore, we can cancel out, we can neglect the presence of air resistance. So the first characteristic that I told you about is going to be that we are neglecting the effect of air resistance. We are canceling out the presence of air resistance. We are considering that the object which is undergoing a free fall motion is going to be encountering very minimal resistance from air molecules, and therefore air resistance is going to be cancelled out. So the very first characteristic for the state of free fall is for the drag forces to be equal to 0, and the drag forces in that case are none other but air resistance. So in order for the condition of a state of free fall to be applicable, the drag forces should be equal to 0. Now, what would be the second condition in that case? Since the drag forces are equal to 0, as we have seen over here, we had the linear relationship between the velocity of the object which is undergoing a free fall motion and time. So if we cancel out the drag forces altogether, therefore that relationship over here is going to remain linear. And if it's going to remain linear, therefore that object over here which is undergoing a free fall motion is going to have a constant acceleration that entire time. But moreover, since the only force acting upon that object is going to be none other but its own weight, therefore its acceleration is going to be none other but the gravitational acceleration. So for the second characteristic over here, we can deduce that any free-falling object, regardless of its weight, regardless of its density or of its shape, if it's being acted upon only by its own weight, therefore all free-falling objects are going to be accelerating downward at the same rate, meaning that all free-falling objects have the same downward acceleration, which is none other but the gravitational acceleration. So over here we can deduce that all free-falling objects are accelerating downward at the same rate, which is none other but the acceleration of gravity, or the gravitational acceleration, which is g equal 9.81 meters per second squared. But that condition over here is applicable for a very specific, for a very particular case, which is for air resistance to be negligible. So we are neglecting the effect of air resistance in that case, and we are considering that the only force that are acting upon all free-falling objects is none other but their own weight. For example, if we consider over here a brick of 1 kilogram and another brick of 10 kilograms, and both bricks are undergoing a free fall motion. But more importantly, we are neglecting the presence of air resistance. So we are considering that the free fall motion for both bricks is actually being done in an isolated environment, an environment where you don't have any drag forces acting against them. Therefore, for the first brick, we have only one force acting upon it, which is none other by its own weight, W1. And for the second brick, we also have one force acting upon it, which is none other by its own weight, W2. So for the first brick, the magnitude of W1 would be equal to M1 times G, which is equal to 1 kilograms times 10. Over here, I'm going to take G to be equal to 10 simply for the sake of simple calculations later on. So the weight 1 would be equal to 10 newtons. And over here, the magnitude of W2 would be equal to M2 times G, which is equal to 10 times 10, which is equal to 100 newtons. So we have found the magnitude of W1 and the magnitude of W2. Now what we need to do is we need to find the acceleration of the first brick, the acceleration at which the first brick is moving down, and the acceleration at which the second brick is moving down. So to do so, we are going to be applying Newton's second law. It states that the summation of all the forces which are acting upon that object is equal to ma. But there is only one force acting upon that object, which is none other but W1. So W1 is equal to ma, and W1 in that case is none other but 10 newtons. Therefore, the acceleration is equal to W1 over m, which is equal to 10 newtons over 1 kilogram. And therefore, the acceleration is equal to 10 meters per second squared. So that would be the acceleration at which the first brick is accelerating downward. It's undergoing a free fall motion. Now regarding the second brick over here. So in a similar manner, summation of all the forces is equal to W2, which is equal to ma. It's M2a. Over here M1a and over here M2a. Therefore, the acceleration of that second brick would be equal to W2 over M2, which is equal to none other but 100 newtons over divided by 10 kilograms. Therefore, A would be equal to 10 meters per second squared. So what can we deduce from these two cases? That regardless of the weight of the brick or regardless of the weight of the object, whenever you have an object undergoing a free fall motion and in the absence of drag forces, therefore these objects are going to be accelerating downwardly at the same rate. They all have the same acceleration, which is none other but the gravitational acceleration g. And this is going to be mainly the focus of our study of today. We are going to be studying the free fall motion in an isolated environment, so we can neglect the presence of air resistance. And therefore, theoretically, And experimentally, we should be finding out that the acceleration of an object undergoing a free fall motion is actually going to be equal to the gravitational acceleration. Moreover, since we are studying the motion of a body which is moving under constant acceleration, therefore we can describe the motion of that body by using the kinematic equations. So what are the kinematic equations? So the kinematic equations, they are equations of motion, meaning that they are equations that describe the motion of an object. However, for these kinematic equations to be applicable, that body has to be moving under constant acceleration. It has to be moving at a constant acceleration. Basically, there are four kinematic equations. You have an equation which is related to velocity, another two equations that are related to displacement, and one equation which is a time-independent equation, meaning it's an equation that does not depend on time. But in our case today, we are going to revert to only one equation, which is the velocity equation, which is an equation that relates the velocity of an object to the time and to the acceleration of that object. And that equation is given as v equal to v0 plus a times t. So the final velocity is equal to the initial velocity plus the acceleration times time. However, in our case, the free fall, the body which is undergoing a free fall motion is going to be dropped from rest. So if it's going to be dropped from rest, meaning that the initial velocity is actually zero. So over here we can cancel v0 out, and therefore the final form for the equation would be equal to v equal to a times t. So we are going to be studying that relationship between the velocity of an object undergoing a free fall motion and its acceleration. So we are going to find out later on that acceleration over here is going to be none other but the gravitational acceleration. And like I said, that condition would be only applicable if the drag forces acting upon the object are very minimal. Regarding the experimental setup of the free fall motion, it consists of the following parts. First off, over here you have the photogate timer. The photogate timer is actually equipped with a sensor. So when you block the passage of the sensor over here, it immediately turns on. And whenever you remove that block, it's going to turn off all over again. Then over here you have a picket fence. The picket fence, it consists of multiple bands. You have transparent and opaque bands. However, that sensor over here is going to be only detecting the opaque bands or the black bands. So in that case, whenever you are dropping that picket fence through that photogate timer over here, that sensor is going to be recording only the black parts. And therefore, it's going to be calculating the time it takes to cover each opaque part. Moreover, that photogate timer is going to be connected to a science interface over here. And the role of the science interface is to collect all the data that is being recorded by that photogate timer in terms of distance and in terms of time. So it's going to be collecting the data or the time it takes each opaque part to travel through that photogate timer. In addition, over here we have a free fall motion software. So that interface is going to be connected to that free fall software on the computer. And therefore the data which was collected by the science interface in terms of time and in terms of distance is going to be transferred toward that free fall motion software. And the free fall motion software in that case is going to be calculating the speed, which is going to be the speed it takes each opaque part on that picket fence to travel through that photogate timer. So let's have a quick run in order to show you how the experiment works. So over here, at the same time, while you are clicking on record, you are going to be releasing that picket fence through that photogate timer. So at the same time, once you click on record, you are going to release the picket fence through that photogate timer. And then you click on stop over here. So as we can see, over here we have multiple values for time versus speed, or speed versus time. The speed is going to be the y variable in that case, and time is going to be the x variable. And the speed in that case is going to be the speed it takes each black part on that picket fence to travel through that photogate timer. So what you are going to do in that case, on the lab report over here, you have the first column, you have the first two columns, which is for trial one. So on the first two columns, you are going to be recording the values for velocity versus time. So over here, you are going to be recording whatever values you have obtained for velocity on that free fall motion software versus the corresponding time. That would be trial one. Then in trial two, you are going to repeat the same thing all over again. So over here, you are going to click on delete last run. Then simultaneously, once you click on record, you are going to be holding the picket fence right above the photogate timer. and then you are going to release it. And then you click on stop again. Same thing all over again. Over here you have values for speed versus time. You are going to record these values in trial 2, and then you are going to be repeating the same thing all over again for trial number 3. Okay? Now, if you look at question number 2 over here, in question number 2, they are asking you to use linear regression. So you have to apply the same method that we have learned during the introduction session. You have to apply linear regression on the calculator in order to find the slope. The slope of what? The slope of velocity versus time. So in that case, velocity is going to be the y variable and time is going to be the x variable. So on the calculator, whenever you click on mode stat and you choose a plus bx, in the x column you are going to be entering the values for time, and then in the y column you are going to be entering the values for velocity. And that would be for trial number 1. And then you find the slope. Then you have to repeat the same thing for trial number 2. You are going to find the slope for velocity versus time for trial number 2. Then you have to find the slope for trial number 3. So in total you are going to be finding 3 values for slope. Now in question number 3 over here, they are saying that you need to find the average value of the gravitational acceleration. So why are they bringing up the gravitational acceleration in that case? The velocity is actually connected to time by v equal to a times t. So like I said before, velocity is going to be taken to be the y variable, and time is going to be taken as the x variable. So in that case, whatever term that you have left, which is multiplied by the x variable, is going to represent the slope. So the slope in that case, it represents the acceleration. But more specifically, that acceleration is going to be none other but the gravitational acceleration. Since we are studying a free fall motion, and more importantly, we are neglecting the effect of air resistance. So in that case, the slope, which is equal to acceleration, it should be equal to g, the gravitational acceleration. So in that case, in part number 3, they are asking you to find the average value of g. So in part number 2, you have found 3 values of slope, meaning 3 values of the gravitational acceleration. So in that case, g bar will be equal to the sum of the 3 values of g divided by the total number of trials. But more importantly, they are asking you to find the RMS error, which is the root mean squared error. In other words, they are asking you to find the error on the average. So in that case, you are going to be applying the standard deviation method on the calculator the same way that I have taught you before. You are going to be choosing one variable, mode stat one variable. You are going to be plugging in the 3 values that you have for g, and then you are going to find the standard deviation of the population, sigma x. Once you find sigma x, therefore the root mean square error, or the error on the average, will be sigma x divided by square root n minus 1.